Just so you guys know, this is being recorded, so don't say anything silly you don't want repeated, because my fourth grade class is just going to use the recording rather than me being on here twice. If you guys have a question, feel free to raise your hand and let me know. I'd be happy to answer it. But what I'm going to do is I'm going to take you guys through the notes for today and through the article as well. And then you guys are going to finish up with a web quest and an exit ticket. Please make sure that you put your name on stuff and turn in both the web quest and exit ticket, whether or not you get them finished. Because if you don't turn it in with your name on it, you're not getting marked present for today for first period. So that's how attendance is being taken. So without further ado, let's go ahead and get started on the notes. Last week, we finished up talking a little bit about heat and how heat affects the atmosphere, how it moves around the atmosphere. And we talked a little bit about air pressure, but today we're going to get into a more in-depth look into air pressure. And we're going to focus on how that creates things like wind and how we read that wind, because that's going to get us into what we're talking about later in the week when we get into weather prediction. So let me go ahead and share my screen. Okay. Everybody can see that okay? Someone give me a thumbs up. Okay, good. Thank you. All right. So like I said, today we're going to talk about air pressure. So first off, we need to remind ourselves that air pressure really depends on how big the planet is. We could talk about air pressure here on Earth, which we're going to talk a lot about, but we could also talk about air pressure on other planets. It all has a direct correlation to mass and gravity, right? A lower mass world is going to have lower gravity, and therefore they're going to have less to almost no atmosphere. But the bigger the world, the more the mass, the higher the gravity, and it's going to have a much thicker atmosphere as well. So gravity and pressure, really the air pressure depends on how much gas there is, and that is usually in direct correlation with how big or how massive the planet is. Want to go on that slide? Okay. Okay, so the stronger the gravity, the more gas that's held by the world, and the greater the weight of the atmosphere on a point, because that's what air pressure is. Air pressure is literally the weight of the air pushing down on your body. So we experience pressure a lot more when we swim in water. If you ever swim down to the bottom of a pool or swim down deep into a pond or something like that, and you hear that ringing on your ear, you feel that physical pressure of the water pushing on your body. The same thing is true of air, except we don't really notice it that much. Number one, because it's equal in all directions, but number two, because it doesn't change that drastically. But the air is actually pushing on your body, just like when you swim down into the bottom of the pool, and the water is also pushing on your body. So the same thing is true because they're both fluids. Remember, water is a liquid fluid, gases are a fluid as well. So the air is just fluid of gases, and that air pressure is just literally the weight of the air on your body. Okay. We know that Earth's atmosphere is about 10 kilometers thick. And we know that our atmosphere is mostly nitrogen gas. Remember, about 78% of it is nitrogen gas and 21% of it is oxygen. And we have to remember that the air is made up of molecules. I know we don't think about it that often, but what we can see here is the blue molecules are all nitrogen gas, and the red ones are oxygen. Remember, everything else in the atmosphere makes up 1%, less than 1% of the air that we breathe. So this is what the air actually looks like if we were to zoom in on it and see the actual atoms. So because atoms have mass, the gravity is going to act on them, and gravity is going to pull the air molecules towards the earth, and that gives them weight. And the weight of the air molecules all around us is what we consider to be air pressure. It's the weight of the air. We also learned last week that air pressure is definitely affected by how high or how low you are in the atmosphere, by altitude. So if you're at a higher altitude, there's going to be lower air pressure. This is because there's physically less air molecules above you pushing down on your body. But what that also means is that if you're at a lower altitude, rather, you're going to experience a higher air pressure because there's more air above you pushing down on your body. So we remember, as you go up in the atmosphere through the troposphere, stratosphere, mesosphere, thermosphere, and exosphere, remember that pressure always decrease, 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 and that's just because there's physically less air molecules above you. This also means that the lower you are, like closer to sea level or below sea level, the more air that's stacked above you, and so you're actually going to experience a little bit more air pressure. Again, you won't notice it that much, that change. We do notice changes in air pressure if you've ever been in a plane or driven up a big hill or like mountain or something like that and your ears pop. That's your body adjusting to the change in pressure. But normally, typically on a day-to-day basis, we don't really experience that much change in air pressure, and so we just don't notice it. But when it's a quick change, like I said, if you're on a plane or driving up a mountain, your ears pop, that is your body adjusting to the differences in air pressure. It's important to understand that for the atmosphere, it's mostly has to do with how high or low you are in the atmosphere, but gas pressure also depends on density and temperature. So if you think about a closed system like a balloon, as you add in more air molecules, they're going to be pushing up against each other and pushing up against the side of the balloon more, so it inflates. So that increases air pressure, adding more air into the system. Or another thing that you could do is you could add heat, because heat is going to, remember, heat is energy. It's going to cause those molecules to speed up. And as they speed up, they're going to move around faster. They're going to hit the sides of the balloon harder, and they're actually going to push it out and cause it to expand a little bit. This is why if you've ever left a balloon or let's say like a basketball outside in the fall or on a cold night, you come out in the morning and it appears to be a little bit flatter. It doesn't actually have any less air in it. It just had that air has less energy, and so it's not pushing on the sides of the balloon or basketball as much. The worst thing you could do would be to fill it up with more air and then bring it inside, because what happens when it heats up is it's going to expand more, and that causes it to pop. So temperature also can influence how much air pressure there is. Everybody good so far? Okay. Now, air pressure is equal in all directions. So again, that's another reason we don't feel it pushing us down, because it's not just down, it really has to do, it's equal in all directions. And so that's important to understand. So if it were just down, we would actually feel the weight of the air, but because it's actually pushing on our body in all directions, we don't really notice the air pressure that much. now remember, as you go up in the atmosphere, as you're higher elevation, the barometric pressure goes down. We call this an inverse relationship. So the higher you are in the atmosphere, the less pressure you're going to experience. Now I added a word in there, and that word was barometric. And what that means is that it was measured with a device called a barometer. Okay, a barometer is used to measure air pressure. And we're actually going to get into how a barometer works. This next part is not in the notes, it's just a little extra history behind the barometer, and then I'll let you know when the notes should pick back up. But air pressure today, we measure it with a barometer. Now, the first air pressure that was measured by a gentleman with the name of Evangelista Torricelli, and he was the person that actually invented the barometer. So let's take a look. And like I said, this isn't going to be in your notes, so just give me your attention up on the screen for this part, and then I'll tell you when the notes pick back up, okay? So Torricelli's barometer was actually ingenious. He used a bowl of mercury. Now, mercury is a liquid metal, and it's very, very susceptible to changes in pressure. So what he did was he suspended a tube in the mercury, and what would happen is as the weight of the air was added, it would push down on the mercury, and the mercury would get pushed up in the tube in an equal amount. So again, the weight of the air would push down on the mercury in the bowl, and that would cause it to rise up in the tube. And so this is why sometimes it's reported in inches of mercury, which we don't really use anymore. But this was actually a really ingenious method, because if there was less weight on the air, there would be less force down on the mercury. And so it would actually cause this barometer to drop, right? Because it wouldn't be pushed up as high, but added pressure, more weight would cause it to rise higher. So this is actually a very, very good way to measure changes in pressure. So like I said, the more pressure there is, the more it gets pushed up into the tube. And he would just put little markings on here to measure in inches how much it rose or fell on a given day. Because the pressure, it does change, because remember, it is affected by things like temperature and stuff like that. So the pressure does change. And we're going to learn about what changing pressure means in terms of the weather as well. Now, why was this really good? Because it was a very simple instrument to construct. And it was very, very accurate. Now, who can tell me why may have this been bad? Why was this not the greatest idea to measure air pressure? What do we know about mercury? Ben? Yeah, it's extremely toxic. So as you can imagine, Torricelli didn't have the greatest death. He did suffer from some mercury poisoning. So mercury is very, very toxic. It's also why we don't use it in our thermometers anymore. We use kind of an alcohol-based solution that does the same job, because we found that, when the thermometers would break, because they were glass, they often broke, the mercury would leak out. And like I said, very, very, very toxic stuff. You don't want to touch it. You don't want to breathe it. And the glass is very fragile. So even though it was very accurate, we've obviously made some changes to this. So this is where the notes are going to pick back up, guys. All right, so obviously we don't use mercury anymore. We use something called an Aronoid barometer. Now this is good because there's no tubes, there's no chemicals, there's no batteries. It's literally just a cell of air. We're going to see that in the next slide. So an Aronoid barometer is what we currently use to measure the air pressure. So this is how a barometer works. Okay, in the barometer you have a cell, which they've taken out most of the air. And because they've taken out most of the gas molecules from that cell, again, it's very susceptible to the pressure around it. And so what happens is, as the air pressure increases, it's going to push on the cell because there's less gas in there, and that's going to cause the needle to rise. As pressure decreases, that cell is going to expand, and that's going to cause it to drop. So a drop in pressure is going to, because that cell can expand more because there's less pushing on it, but an increase in pressure means it's going to contract, it's going to push on that cell, it's actually going to cause that needle to rise. Now, television, if you ever watch the news or something and you hear weather forecasters, they're usually going to give pressure in inches of mercury, even though we don't use that anymore. Meteorologists, you're going to hear a better term called millibars. However, millibars is more of our system. In the article, we'll see that there's another unit that's used for the metric system. We're not going to use it as much. We're going to focus on millibars for this unit. So we'll talk about pressure in millibars. All right, there are two different types of pressure. Two different types of pressure measurements. There is what we call station pressure, and that's if you're at any given spot, you're at a weather station and you're measuring the pressure at that specific location, that would be considered a station pressure. That is unique to where you are on the planet, okay? Because remember, we don't all live, we don't all live at the same altitude. So obviously, if we want to start comparing pressures in different areas, the station pressure is not going to be a very good measurement to use because it's going to be affected by how high up in the atmosphere you are or how low you are. For example, Denver, Colorado is called the Mile High City because it's a mile above sea level. So obviously the pressures there are going to be much, much different than the surrounding area because it's so high up in the atmosphere. So what we can do to compare different pressures of different areas is we can kind of adjust it to a baseline. And what that's called is sea level pressure. And so what they do is they adjust it to what would the pressure be like if it were at sea level. And that allows you to compare air pressures anywhere in the world because it kind of brings them all to the same metric, all down to sea level. So even though that's not what you experience, like if you were in Denver, Colorado, you would still be able to compare Denver, Colorado to say, let's say Richmond, Indiana, even though we're not at the same elevation, just because we bring it, both pressures would be brought down to see what would it be like at sea level, and then you can get a good comparison of how the differences in pressure between the two places. Now, what does a change in pressure mean? Well, remember, we're getting into discussing weather. So a rising barometer, the barometer that's going up, is an increase in pressure. And this usually means that we have fair weather coming ahead. We really like high pressure systems because it's clear skies, generally cooler temperatures, less humidity, things like that. So it's going to be really nice weather. So if you see that barometer increasing, you know good weather is coming into an area. So if you see a barometer increasing in pressure, that means good weather is moving into the area. There are certain parts of the country that get high pressure systems more often. For example, California usually gets very high pressure systems coming through. That's why California is known for their nice fair weather. Not a lot of clouds, not a lot of rain, just kind of nice, calm, clear weather. Okay, is everyone good on this one? And there's a bit more to write for this slide. Okay, so if a increase in pressure means good weather, well, obviously a decrease in pressure probably means bad weather is coming our way. So a falling barometer or a decrease in air pressure usually means that a storm is going to come through. How low the pressure is will kind of depend on or cause differences in how fast the wind speeds are and how bad the storm is. but any drop in pressure usually means it's going to be a little more cloudy and possibly storms. In fact, the lowest pressures that we can find on Earth are on the insides of tornadoes and hurricanes. They could produce very, 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 very low pressures. Obviously, you can, it kind of makes sense because the air is kind of being pulled apart in the middle. It's being pushed outward. And so the air pressure is going to get very, very low at the center of those. All right, and as you guys finish that up, this should be the end of the notes. So Darlene, would you please pass out the reading article to the students?
Reading article?
There should be a, let me put it up on the screen. Where? It should be understanding pressure gradients.
Okay.
Look like this on the front page?
Yep.
Okay.
Got it. Okay, they're passed out.
Okay, awesome. Okay. All right, ladies and gentlemen, so what we're going to do now is we're going to read through this together because there's some vocab words that are a little bit strange, and I just want to make sure we can pronounce them all correctly. And this is going to get into those high pressure and low pressure systems and how they affect the weather. Then later on, as you can see, we're going to start looking at some maps of the United States. And what we see here up on the screen is the barometric pressure map. So we're going to be looking at this, how to read it and how to figure out what's going on with the pressure. Okay, so follow along with me. You might want to underline some stuff as we go through. Again, feel free to ask questions as you guys, as they come up, if you need something explained further or whatnot. But here we go. Understanding pressure gradients. Atmospheric or barometric pressure is the weight of the atmosphere. The atmosphere is about 20 miles thick, so there's 20 miles of air stacked up over our head. The air actually gets thinner as it goes up, so most of the weight comes from the first few miles above the Earth. We know this, right? The troposphere is the most densely packed layer of the Earth's atmosphere, so obviously that makes sense. Most of the weight comes from troposphere. Okay, the actual atmospheric pressure works out to be about 14.7 pounds per square inch. We call that 14.7 PSI. That's pounds per square inch, PSI, at the surface of sea level. It could also be called one standard atmosphere because that's our atmosphere. So if we're judging atmospheres on different planets, we might talk about how many atmospheres, more atmospheres it is than Earth's, or how many less. So we can call it one standard ATM, one standard atmosphere of pressure, since it's the amount of one of Earth's atmospheres. All right, the National Weather Service reports surface air pressures in inches of mercury, while air pressure aloft, means elsewhere, is reported in millibars. 1013.25 millibars is the standard sea level pressure of Earth's atmosphere. The metric system's unit for pressure is called the Pascal, with 1 millibar equaling 100 pascals, or 1 hecapascal, or 0.1 kilopascals. Scientists generally use hecapascals to measure air pressure, although you'll sometimes see them in centimeters of mercury, especially on older barometers. The term hectopascals is replacing the term millibars. We're still going to use the term millibars for this class. Okay, we're not going to use hectopascals. All right, let's see what high pressure is about. High pressure areas form when an air mass cools over cool land or ocean surface. The cooling causes the air layer to shrink, becoming slightly thinner. This shrinkage then causes the surrounding air in the upper troposphere to fill up the extra space. The added weight of the extra air causes higher pressure at the surface. The higher pressure air at the surface then tries to flow outward towards lower pressure. High pressure is generally associated with fair weather, and low pressure is generally associated with cloudy skies and precipitation. So let's pay close attention to this graph right here, or this little diagram right here. So what's happening is when air is cooled, because it moves over cool land or cool ocean water, we know heat goes from hot to cold. So the heat from the air is going to go into the ground, and that's going to cool the air temperature. If you take away its heat, you're taking away its energy, and so the air molecules actually get closer together. They get more closely packed, more densely packed together. So it's going to shrink. And this, if you guys see these arrows are the extra air that's coming on top of this, that's being stacked on top of that shrinking air. So there's physically more air above it that's adding to the weight down below. So that's why high pressure is at this cooling causes high pressure rather, because the cool air takes away the heat, the air mass shrinks, extra air takes up that space on top, and that adds to the weight of the air. And guys, because the air is sinking, because it's cold, it's more dense, it's sinking, you're not going to get the formation of clouds and stuff like that. That has to happen when the air is rising. So the cool air sinks, and so that's why it's usually associated with really nice weather. And then at the surface, the air is going to go outward, because remember, heat went from hot to cold. Things like to go from high to low. So in this case, we're going to go from high pressure, and it's going to push out to areas of lower pressure. It wants to spread out. So now let's take a look at what happens with low pressure. Low pressure areas form when an air mass warms, either from being over warm land or ocean surface, or from being warmed by condensation of water vapor in large rain or snow systems. I'll explain what that means in just a moment. The warming causes the air layer to expand upward, becoming slightly thicker. This expansion then causes the air in the upper troposphere to flow away, leaving less mass and so less weight or pressure at the surface. The lower pressure air at the surface then causes the higher pressure air around it to flow towards the low pressure. Lows are frequently associated with stronger winds and atmospheric lift. Thus, low pressures typically brings cloudy or overcast skies. The lowest pressures on Earth are at the centers of hurricanes and tornadoes. Okay, so obviously it makes sense that the air can pick up heat from being over warm land or warm ocean surfaces. But let's talk about the second part. The condensation of water vapor in large rain or snow systems. So as water falls out of the air, either as rain or snow, what that means is the heat has left the water and it's gone into the air. So that it's actually heating the air. So as it's snowing or as it's raining, the heat is leaving the water vapor and it's going into the other air molecules. And that's what's causing the water vapor to condense and fall out as rain or snow. So it's really hard to think about, but as it's raining or snowing, the air itself is actually getting slightly warmed because it's absorbing the heat from that water vapor. Now guys, make sure you're turned over to the second page so you can see this diagram that I'm going to talk about right here. Everyone there? Okay, so in low pressure, as it moves over warm land or warm water, that heat from the land or water is going to go into the air. Remember, heat is energy, so that's going to cause those air molecules to speed up, and it's going to cause them to spread out, take up more space. And that pushes away the air in the upper troposphere. So that's what these outer arrows are. So as that air expands, it takes up more space and it pushes the air above it away. So now there's less air above that spot. And so that's what's causing the lower pressure. And because that air is expanding, it's warm, it's rising, it's less dense. If it has any water vapor at all, as it rises, that water vapor is going to start to condense. And this is why we get clouds and possibly storms, because all that air is rising. Remember, high pressure, the air is sinking. That's why there's no clouds. But in low pressure, the air is rising. And that's what's causing the clouds and stuff to form. And because air goes from high to low pressure, at the surface, the air is going to be spinning inward towards the low pressure center. Okay, let's keep reading. As in most natural systems where there's a tendency towards equilibrium, that just means things want to equal out, air moves from high to low concentrations. Please highlight that or underline that or circle that. Air moves from high to low concentrations. That's very important. In other words, air moves from areas of high to low pressure. The speed of the wind is determined by the pressure gradient. Wind speed is directly proportional to the size of the pressure gradient. So what that means, if there's a really big change in pressure, there's really high and really low pressure close together, that wind is going to be very strong because it's like a big downhill. It's a big push from the high pressure to the low pressure. If it's just slightly higher and lower pressure, there might be a gentle breeze, but there's probably not going to be very much wind at all. So the bigger the difference between high and low pressure, the stronger the winds. And the lower difference between high and low pressure, the more gentle the winds. So how do we figure out where wind is going to happen? How do we read these? This is what we're going to get into with the rules for what we're going to draw are things called ISO lines. These are lines that show areas of equal pressure. Okay, ISO lines, areas of equal pressure. And there's a little diagram at the bottom of this page that you can see. All these circles, all these lines, those are ISO lines. So if you notice this big one, you can kind of see this line goes through all the 1004 air pressures around the country. And what this is showing you is we're making a hypothesis, we're making a guess as to about where 1004 exists between these different points, because obviously there's not pressure measurements being taken everywhere. They're just being taken at different weather stations and stuff like that. And then we have to kind of fill in the data. And that's what we're going to be doing with drawing these isobar lines. So what I would like you guys to do is go ahead and flip over to this back page. You guys should see this map on the very back. Someone give me a thumbs up if we see this map on the very back. Okay, thank you, Malia. I think that was a thumbs up. Yes, no, maybe so. Okay, thank you, James. All right, so we can see this map on the back, and what we're gonna do is we're gonna draw the isobar lines. Now, there's not a really easy way for me to do this on here, unfortunately. Let me try one more time to copy this into PowerPoint because it'd be much easier for me to do if I could do it in the PowerPoint. Really, you won't. Why won't you? Oh, that's a lie. All right, let me just open up a new one. Okay, so let me bring this up on the screen. All right, so now I'm going to be able to draw on this with you guys, which is good. Okay, so what we have to do is we see a map, and we see a whole bunch of numbers on this map. And what these numbers are the different air pressure measurements from around the country. And what we're going to do is we're going to read this and interpret this to figure out where's the high pressure, where's the low pressure, and where's the wind going to occur. So let's start with the smallest. What is the smallest number you guys see on this map? $996, exactly. So if we look over here, kind of in the Mideast, we see 3 996s, okay? If anyone's ever played Connect the Dots, this is exactly what we're about to do. So I'm going to take a line, and I'm going to draw this line, maybe. Hello? Oh, why is it drawing over there? Uh-oh. Let's erase that. Okay. Let me try and draw it. Maybe if I do it over here, it'll work out. All right, but what I want you to do is just connect the dots. If this doesn't work for me. Oh, there we go. Okay, so I'm going to take 996. I'm going to connect all three of those to make a loop. So go ahead and do that on your paper. Go ahead and connect all those 996s to make a nice little loop. Now, what's the next highest number that we see above 996? The next highest number would be 1,000. Now, here's an issue. I see some 1,000s. Here, let me pull up my laser pointer so you guys can see where I'm pointing again. Okay, so I see some 1,000s around here, right? You guys see these numbers, but then I also see some 1,000s over here. I'm actually not going to connect these because if you notice in between these two, there is 1,004. Now, what this line means is everywhere along this line, there's 996. When I make 1,000 line, that means everywhere that line goes, there's an air pressure of 1,000. I can't make my 1,000 line cross my 1,004 because you can't have two air pressures at the same location. Obviously, there's some higher pressure here, and then it starts to decrease afterwards. So we're actually going to make this a separate line. So when I make my 1,000 line, I'm just going to include all the thousands on the right side. And then I'll get back to these a little bit later because they're not connected. So let me go ahead and get to my pen. And what I'm going to do is I'm going to make a little loop. I'm going to connect all these 1,000s. And my loop's pretty bad because I'm done on PowerPoint, but you guys get the idea. Your loop should go through this 1,000 in South Carolina as well. Mine does not. Let me erase that and try again. Go. Try this one again, get a little bit closer so you guys can see what this should look like. No, that's the wrong thing. What's up?
Having some trouble.
Yeah, I'm having some trouble. There we go. So now all my thousands are connected. And so I'm going to go to the next highest number, which is 1,014. Now, if you guys notice, there's no measurements on this right side of the paper. Why? What is to the right of our circle? So I'm talking about this area over here. Why aren't there any numbers over here? Why aren't there any numbers down here? What is this over here?
Sea level.
It's what?
Ocean, sea level.
It's the ocean, right? So there's no weather stations over the ocean. So we don't have any numbers here. But does that mean that 1,004 millibars of pressure doesn't exist here? Of course not. It has to exist somewhere. And so again, we're going to estimate this line as we draw it. And as we connect all these 1,004s, we're going to have to estimate about where that pressure is going to be. So it's not going to be exact, but that's okay. So what I'm going to do now is I'm going to go around and I'm going to connect all my 1,004s. Make sure you make it all the way up to Maine, all the way around, and then back to Florida. And this is what you should have on your paper, is a line connecting all the 1,004s. Now, again, there's some 1,004s on the western side of the country, but there's that 1,000 line in between. And so that's actually splitting my weather systems. I can't connect this line through there because I can't have 1,000 and 1,004 pressures at the same point. That doesn't exist. So now I don't see any bigger around my 1,004. So now it goes back down. And so what I'm going to do is I'm just going to make a line. Oops, that's terrible. Let's try that again. I'm going to make a line connecting all my 1,000s. If my map was big enough, it's important to understand, if my map was big enough, I would connect these into a loop. These all form loops because somewhere there's going to be 1,000 pressure, but I don't have enough information. And so I'm just going to make a straight line separating my two weather systems. Now on the left side of the map, I see above 1,000 is again 1,004. So I'm going to go ahead and connect those. Okay, I'm going to take mine off the map because obviously that pressure exists somewhere. We just don't have that information. Off the western coast is the Pacific Ocean, so we obviously don't have measurements over there. The next highest one above 1,004 is 1,008. So I'm going to connect all of those. Okay. And then I see 1,012 is my next highest. I'm going to connect those. I'm going to make this a nice little circle. And then 1,014, there's only one point there. And so that's my highest pressure on the entire map. And so what I'm going to label here at 1014 is I'm going to put an H. And why am I putting an H there? Well, because that's my high pressure center. And I'm going to go back over to the right side, and in the middle of this 996 circle, I'm going to put an L, because this is my low pressure. Okay, so there's my low pressure center. And so what I can see here is now I have a good reading of the different pressures around the country. And we know the wind is going to go from where to where. It goes from high to low. So I could put some big arrows here to show that the air is going to be moving in this direction, because again, that's probably not the best thing to do in the same color. Make that a different color so you guys can see those. Oh, I lost one of my circles. Struggle is real today, guys. Put that circle back. There we go. Okay, let me change my color so you guys can see these arrows that I'm making. Okay, so again, it's going to go from high to low pressure. So this is the direction that the wind is moving in the country at this time. So that means for West Virginia, what would the weather be like over here in West Virginia? So I'm right here at this low pressure. What's the weather going to be like here? Say again.
Is it stormy?
Yeah, it's going to be stormy right there because of that low pressure, right? So there could be some rain or some snow, depending on what season it is. We can't tell what the temperatures are with this. We can't tell what season it is. So we don't know, but we could expect some precipitation there for sure. It's definitely some cloudy skies, some possible rain or snow. And what's the weather like over in California?
Clear sky.
Yeah, clear skies, fair weather. All right, this is the good weather right here, because high pressure, the air is sinking, right? No clouds, so clear skies and low precipitation. So this is what weather people, because it could be men or women, weather people do. They take the information on the map and then they kind of read and interpret what it's going to be like. And this is how we can see. So this is obviously on the a bigger scale, the country scale. We can also do this more locally and have more detailed information, but this is generally what we can use to see the major weather patterns in the United States for any given day. So I can see a low pressure system here, high pressure system here. And obviously this is a very simplified map. It gets much more complicated than this. There's more than two pressure centers. Sometimes you can have multiple high pressures or multiple low pressures on the map at a given time. But this is just kind of generally what we can do to interpret what the weather is going to be like using this type of information. So again, these lines are called isobars, and they show areas of equal pressure. So on one side, it's going to be higher, and on the other side, it's going to be lower pressure. So these lines just show where that pressure is going to exist. So what you guys have left for today, oops, sorry, let me go back to that. Discard. Okay. So what you guys are going to do now is you do have a couple questions, just these 5 analysis questions. So do your best to answer these. If you need to pull up a map of the United States because you don't know what these states are, please do so. And then all you have left after this is the Wind Web Quest. So once you get these done, go ahead and ask Darlene for the Wind Web Quest, and she will give that to you. You guys can either use your phones or you can use a Chromebook. If you use a Chromebook though, please make sure you put it back and it's plugged in. This is what the Wind Web Quest looks like, guys. It's going to be the first 2 pages. You don't need to do this bottom part. So where it says Coriolis effect, you can actually cross that out. I just want you to do what's in the boxes. So you're going to go to Weather Whiz Kids. I'm going to pull that up so you guys can see that real quick. And I can show you how to navigate this site before I set you loose. You're going to go to weatherwizkids.com and you're going to go to weather, and then it's going to drop down. You're going to go down to wind. Okay. And when you click on wind, it's going to take you to the wind information. They've got some little articles, some pictures, some videos and stuff like that. And what you guys are going to do is there's different sections. So if you look here on the left side, I have different sections. So when you guys answer the rest, get down to the bottom, you've answered all those questions, then you're going to click on the next section. Okay. And now you get to global wind patterns, and we'll talk about the global wind patterns. And then you click on types of wind, and it'll give you the types of wind. So just remember there, once you get to the wind page, there's also these little sub pages here for you guys to help answer some of those questions. Okay, most of it should come from the first wind page, but then you'll click on these for the global wind and other stuff like that. So guys, you got about 40 minutes left of class. So that should give you a good head start on the wind web quest. You may not get it all the way done, but I still want you to turn it in so I can see how much work you got done in class today. And there will be an exit ticket as well. So if you get done with the wind web quest early, you can ask Darlene for the exit ticket, but both the wind web quest and the exit ticket need to be turned in before you leave, whether or not you finish the wind web quest. Okay. Are there any questions? Okay, I hope to be back tomorrow. The only thing that would remove me from that is if I'm gonna go get a COVID test. So if that shows up positive, obviously I won't be in, but I think it's just like a severe cold or something like that. So I should hopefully be able to come back tomorrow. I do have your test graded overall. People did a good deal better on this test than they did on the first test, so that's good news. We'll talk about test grades and current grades once I get back later this week. Okay. Thank you guys for your hard work today. Darlene, thank you for covering the class, and I hope to see you guys tomorrow.
Thanks, Nick.
Feel better soon.
Thanks, guys.